everyone and welcome back. Today we're going to continue our exploration of intermediate statistics and introduce probably one of the most fundamental and important modeling tools known as multiple linear regression. Up to this point, I'm assuming that you have some basic linear algebra or matrix algebra exposure, at least multiplying by matrices and a couple basic principles, and also you have a working understanding of simple linear regression. With these two things, we'll be able to build all of the multiple linear regression, at least basic principles, and then we'll talk about a couple applications a little bit later. So let's start off by talking a little bit about simple linear regression, since multiple linear regression is just going to be a generalization of that with multiple variables. So let's assume that y is going to correspond to our one response variable. If you have multiple response variables, that is what we refer to as multivariate linear regression, which we'll definitely get to a little bit later, but now we're just going to be working with just one response variable. And that response variable is going to be a function of one explanatory variable, and that's going to be x1. And then we're going to have two parameters, in particular beta 0 and beta 1. So here, this is going to be our one explanatory. Some people will also call it a predictor variable. And this is known as our simple linear regression model. Okay, and typically, or at least sometimes, people will include another term at the very end plus epsilon. This plus epsilon is sometimes referred to as the residual term, right? Because when we try to fit a linear model to a set of data, this line is not always going to fit perfectly. Therefore, there's always going to be some residual between the actual y value and the predicted point, right? So sometimes, to distinguish between, for example, the predicted value and the actual variable or actual value of the response variable, sometimes we will write, for example, y hat to be equal to beta 0 plus beta 1, x1. So this would be our predicted value, where the residual would just be the predicted value minus the actual value. Right, so those are some of the basic principles of linear regression that you probably already know. So now what we're going to do is we're going to extend from one predictor variable to multiple ones. So our model is going to be of the form y is equal to beta 0, our intercept term, plus beta 1, x1, plus beta 2, x2, all the way down to beta p, xp, and then plus our epsilon term. So these are our p predictor variables. This epsilon is going to be our residual term. Same interpretation as before. And we also have our intercept term. And obviously, if I have p predictors and one intercept term, that means I have p plus 1 beta coefficients of my what we call the multiple linear regression model. A couple other notational things, for example, that would just be your model. What about in particular points? So if you want a particular predicted value, for example, the hat value, for example, the predicted value for point 1, that would be the point estimate for beta 0, which we're going to represent by beta hat 0, plus beta hat 1 times the first variable associated to that element in our data set, plus beta hat 2 times x2, that again associated element, plus all the way down to beta hat p xpk. So for example, if you have 50 respondents in your sample set, this would, for example, be the age of the second person, the height of the second person, all the way down to the annual salary of the second person, or the kth person, generally speaking, where each of those p variables represents some predictor that you're trying to represent in terms of what you're trying to predict. So for example, you might be trying to predict happiness with respect to the three predictors: age, height, and annual salary, or something along those lines. Okay, and similarly speaking, the actual value, so yk, would just be equal to beta hat 0 plus beta hat 1 x1k all the way down to beta hat p xpk plus our associated residual term. All right, so what's the difference between epsilon and epsilon hat? So epsilon, that is our true residual, and the epsilon hat, that's going to be our associated predicted residual or approximate residual associated to that particular element. Because what we're trying to do is we're trying to approximate the equation of that line, right? So if we're trying to approximate the equation of that line, this line and the actual line that we're able to generate is going to be a little bit different. So if we were to focus on the same exact point, obviously the residual is possibly going to be a little bit different. Right, so that's just some of the basics associated to multiple linear regression and the notation that we're going to be using throughout this entire video. So there are some assumptions for multiple linear regression that must be met. So assumptions for multiple linear regression. If these assumptions are not met, then we are to say that the multiple linear regression model is not appropriate. So the first assumption that must be met is the linearity assumption. And these assumptions are actually quite parallel to the simple linear regression assumptions. And that is the expected value of the random variable y given some particular value of x1, say x1 is equal to little x1, x2 is equal to little x2, all the way down to xp is equal to little xp, must follow a linear pattern. In particular, there must exist these beta 0, beta 1 down to beta p's such that the mean follows this particular number. And these x2s down to xp's, these are numbers. Right? So that means there exist these beta k's such that this linear relationship between the means follows. The second assumption that must be held in order for this model to be appropriate is what we refer to as the homoscedasticity assumption. And this says that the variance of this random variable y with respect to some given values x1, x2, all the way down to xp must all be equal to a constant that is independent of the x values for which we have chosen. Right? So that's what we call the homoscedasticity term. And the third assumption is what we refer to as the normality assumption. And that is that the random variable y must be associated to a normal distribution with some mean mu, given some values x1, x2 down to xp, and some variance sigma squared with variance y dependent on x1, x2, x3 down to, say, xp. Now, generally speaking, these assumptions are independent of each other, but if all of them are true, we can rewrite mu with respect to this linearity assumption, and if we know that this homoscedasticity term is met, then we can just write that as sigma squared. Now, it's very important to understand that sigma squared and sigma squared y given some sequence of variables x1 down to xp are all different things, so make sure you understand the difference between these three variances. And the fourth assumption is what we refer to as the independence assumption, is that all observations, in particular the observations that we're talking about are the yk, are independent of one another. And as long as all four of these assumptions are met, then we say that a multiple linear regression model is appropriate for our data set. Now that we have some of the basics discussed for multiple linear regression and the four assumptions that a multiple linear regression model should satisfy in order for it to be appropriate, let's just mention a couple other things before we get into the actual derivation and the matrix representation for the multiple linear regression model. So recall that for simple linear regression, the error sum of squares or sum of squared errors or sum of squared residuals, typically those three terms are synonymous, is given by the sum of the squared residuals. More in particular, yk minus y hat k, all of them squared, and then sum all of them up. So if we were to expand this to sort of look like, see what this looks like in the multiple linear regression realm, then it would look like the following. So it's going to be, again, the sum from k is equal to 1 to m of the actual response variable, or value, minus the predicted value. So that's going to be, for example, beta hat 0, minus beta hat 1, x1, the the first value of the kth response, minus beta hat 2 times x2, the second value of the kth response, all the way down to beta hat p times xpk. So that's the pth value of the kth response, all of that the quantity squared. So we want, if we're going to be using a least squares model, we want to find these beta hat 0, beta hat 1s all the way down to beta hat p's such that SSE is minimized. And if you remember how we test the appropriateness of a simple linear regression line in the ANOVA table, the SSE was one of the metrics in that particular ANOVA table. So if you remember, there's another metric called the mean square error term, which is often abbreviated just by MSE, or the mean square error. And that's going to be equal to SSE divided by n minus p minus 1. So for the simple linear regression model, i.e. p is equal to 1, since we had one predictor, we had that the MSE was going to be equal to SSE divided by n minus 1 minus 1, or equivalently SSE divided by n minus 2. So n minus p minus 1 is the generalized version of the MSE. Now, one very important theorem associated with the MSE is actually the following theorem, which I'm not going to prove. This proof is a little bit more time-consuming than I want to spend, at least today. And that is the expected value of the MSE for a sample is actually equal to the sigma squared that is in the homoscedasticity assumption. So in the homoscedasticity assumption, remember that the variance should be equal to the same exact thing regardless of the distribution that we're sampling on, right? So if we sort of look at this from the three-dimensional perspective, so we sample across, for example, x1, x2, down to, for example, xp, and we sample across each of these lines, so the means should follow along a line, and the distribution along each of these should be normally distributed, and the variance for each of these normal distributions should be the same exact thing, right? So each of them have a particular variance, and to estimate that variance, you just calculate the MSE, and that's actually an unbiased estimator of sigma squared. So MSE is an unbiased estimator of our homoscedasticity assumption and variance, which is actually going to come in very handy a little bit later on. So therefore, if our goal is to approximate sigma, that means we can approximate the standard deviation sigma with the square root of the MSE, or equivalently the square root of the error sum of squares, the sum of squared residuals, divided by m minus p minus 1 for the multiple linear regression model. So now that we have a formula for approximating the homoscedasticity variance, now there's one very important question we have to answer. Are there formulas or ways to calculate for the beta case, and moreover the beta hat case, and is beta hat k an unbiased estimator of these beta k's? So that's what we're going to go into right next. So recall that for simple linear regression, if we have a response value and our one predictor value xk, and we have already calculated our beta 0 and beta 1, then, and let's assume that epsilon is the associated residual for that point, then yk can be represented as this particular linear combination. Moreover, I can put a 1 coefficient in front of this. I can actually write it as yk is equal to 1 times beta 0, and I can actually put my xk in front of it and then write my beta 1 at the very end. Now you might be like, well, that's the same exact thing. Why do you choose to write that? That's actually going to make the next extension a little bit easier to see once we switch into vector and matrix mode. So this is going to be true, and this is going to be true for all k is equal to 1, 2, all the way down to n. So therefore I can say that y1, y2, all the way down to yn as a vector is going to be equal to 1 times x1, or 1, x1, 1, x2, all the way down to 1 xn times the matrix beta 0, beta 1, plus epsilon 1, epsilon 2, all the way down to epsilon n. So that is the matrix representation of that expression. And you might be like, well, how is that the same? So the first component, y1, is going to be equal to the dot product of that vector with that vector, which is going to be 1 times beta 0 plus x1 times beta 1, and then plus epsilon 1. So that's going to be the first element. And then we're going to have y2 is equal to the dot product of that vector with that vector, so it's going to be 1 times beta 0 plus x2 times beta 1 plus epsilon 2, and then all the way down to the last element, so yn is equal to 1 xn dot product with beta 0, beta 1, so that's going to be beta 1 plus beta 1 times xn plus epsilon n, right? So that's going to be true for all of those particular expressions. So this is the vectorized version of this expression. So this y vector is going to be our n by 1 response vector, and then we have this n row by 2 matrix, which we're going to be representing just by x, and this is true for one predictor. This vector here, this is going to be represented by the vector beta, and that's obviously going to be a 2 by 1 for one predictor, right? So that's for one predictor only, and this n plus 1 is just going to be abbreviated by epsilon, right? So if I want to write this as a matrix equation in short form, then we have that y is equal to x beta plus epsilon, right? So this is the simple linear regression model for our simple linear regression model, and actually we can extend this for a multiple linear regression model just by increasing those predictors. So let's summarize what that is for the multiple linear regression model, and keep in mind this is a matrix equation. And you cannot write beta in front of x, you can only write it as x times beta. If you know some matrix multiplication rules, you should know why that is the case. So here y is an n by 1 vector, x is going to be an n row by p plus 1 matrix, because we have that column of 1s for our intercept term and our p columns for our predictor values for each of our responses. And then we have beta, that's going to be our p plus 1 by 1 vector, that's going to have our p plus 1 coefficients, beta 0, beta 1 down to beta p, and then our epsilon is going to be m plus 1, and you should be able to see that the matrix multiplication does work out, and also addition for these particular elements. So that is our matrix representation for our multiple linear regression model. Right. And that's true even if you don't want to do your least squares approach for minimization of the sum of square errors, right? So let's assume that we actually want to go about this in the least squared fashion. So our goal is to find our beta, which keep in mind is a vector, that minimizes minimizes the error sum of squares. And keep in mind that this would be a least squares model. If you don't want to do a least squares model, you would have to optimize some other functional, and we'll talk about some variations a little bit on later on. So what is the vectorized version of the error sum of squares? So keep in mind y is equal to x beta plus epsilon, which means that our error vector, or our residual vector, is going to be equal to the vector y minus the vector x beta. So keep in mind x beta is also a vector too. So if this is a vector, we should be able to take the norm of it as well. So that means the norm of that vector epsilon, and let's assume we square that so we get rid of that square root, is going to be equal to the first component squared plus the second component squared all the way out to the nth component squared. And you should be able to see that in summation notation, that's just the sum from k is equal to m of epsilon k, the quantity squared, which is, by definition, the same as the sum from k is equal to 1 to m of yk minus y hat k, the quantity squared, which is, of course, equivalent to the error sum of squares. So that means that the norm of our residual vector is actually equivalent to our error sum of squares. So the least squares model, which goal is to minimize the SSE, is actually has the equivalent goal of minimizing the squared norm of our residual vector. So that's the matrix representation of the same exact problem, but this is a lot more easier to approach because we have multiple variables, right? And keep in mind the SSE in vector form will now be in the form y minus x beta, the quantity squared. So our goal is to minimize this particular functional, this matrix functional moreover. So let's see if we can actually build an alternative representation for this particular functional, and then we're going to do some matrix derivatives of this, minimize, set it equal to 0, and we're going to have an equation for our betas. So if we look at our SSE term, so our SSE again is going to be equal to the norm of y minus x beta, the quantity squared. And keep in mind this is a scalar, a fancy word for a number. So one should remember that the norm of a vector squared is actually equal to x transpose times x. So those two things are equivalent. So I can write this instead as y minus x beta, that vector transpose, times y minus x beta. So once I have that, now I can apply this transposition over the difference of those two vectors, because we know transpositions distribute nicely over subtraction. So that's going to be equal to y transpose, and then we're going to have beta transpose x transpose. Remember, the transpose reverses the order. So we have this particular expression, and now we have a bunch of vectors that we can sort of distribute in our normal way. So this is going to be equal to what? So this is going to be equal to y transpose y minus y transpose x times beta minus beta transpose x transpose y plus beta transpose x times beta. Now keep in mind that this is a scalar as well, and if you have a scalar and you transpose that, that's actually equal to the original scalar as well. So I can actually apply the transposition to this, and it's actually going to give me the same exact answer. So I can rewrite this instead as y transpose x transpose transpose and beta transpose transpose, which is just the same thing as y transpose x times beta, which of course is just going to be the same thing as I have there. So that means this is going to be equal to, and keep in mind this is just the SSE, this is going to be equal to y transpose y minus 2y transpose x beta, and then we have this beta transpose x times beta. So this is an alternative vector representation of the error sum of squares. Now that we have this nice little formula, now we're going to take the derivative, set it equal to 0, and solve for our beta term. So remember what our goal is for this. So our goal is to minimize the error sum of squares with respect to this beta vector. right? And keep in mind this beta vector is a n by 1 vector, right? So that's going to be p plus 1 by n by 1 vector, right? So let's take the partial derivative with respect to the beta vector of SSE. Now keep in mind, SSE is a scalar, so the partial derivative with respect to beta of a scalar and the partial derivative with respect to beta transpose of a scalar are going to be equal to each other. So if you've seen, for example, derivatives with respect to transpositions, they're actually going to be the same thing for scalars. So that's actually a nice thing to keep in the back of your mind when we're actually going to be taking the derivative of each of these terms. So this is going to be equal to the partial derivative with respect to beta transpose, let's just write beta transpose, of y transpose y minus 2y transpose x transpose beta, and then plus beta transpose x times beta, right? So notice that this first term does not have any betas in it. That's just our response vector. So that differentiates to 0. And then this is going to be equal to, so we're going to take the derivative of this. So that's almost like a times beta. And when we take the derivative of a linear term with respect to a vector, we're going to be transposing this term in front. So that's going to be equal to minus 2x transpose y. And then if you remember the derivative of that, that's almost like the derivative of the norm of x transpose x, the quantity squared. Right, so the 2 sort of comes down, and then we're just going to be left with the xtx beta term. So that's going to be equal to plus 2xtx times beta, and then we're going to be setting this equal to 0 and then solving for x, right? So that's just a brief dive into matrix calculus, and you can prove all those things if you want. So notice that there is a 2 on both sides of this expression, so I can write this, for example, as y, or xty, is equal to xtx beta. And our goal is to solve this equation for beta. So if I write this in another way, for example, xtx beta is equal to xty, our goal is to solve for beta, so we need to get rid of this little xtx term. So what I can do is I can multiply both sides on the left by xtx inverse, because that is going to be a square matrix. One should be able to prove that. So xtx inverse, but it's important to note that that matrix must be invertible, but that's going to give our expression of beta. So therefore, we actually have a formula for our beta term. So that means beta is equal to xtx inverse xty, provided that the determinant of xtx is not equal to 0. Okay, so that's very, very important. But keep in mind, we're actually not really solving for beta, we're trying to find the value of beta hat. So now what we're going to do is we're going to go out into our world and we're going to gather a sample from our population, and we're going to get an approximation for this beta, which is going to be represented by beta hat. So let's assume that S is a subset of a population P, and let's assume beta hat is calculated in the same exact way as our theoretical version, xtx inverse times xty, with the assumption that the determinant of xtx is not equal to 0. So a wonderful theorem that we definitely need is that beta hat is an unbiased estimator of our beta term. Because if it's not an unbiased estimator, then we should be looking for one so that we have as minimal error as possible when we're trying to estimate these types of things. So let's actually go ahead and give a quick proof of this. So if beta hat is an unbiased estimator of beta, then the expected value of beta hat should be equal to beta. So what is beta hat equal to? So beta hat is going to be equal to xtx inverse times xty. Now keep in mind the random variable in this picture is going to be y. This is just our explanatory variables, which is just based upon our data set. So those are just constants as far as the random variable portion of our operator is concerned. So that can factor out the expected value. So we're going to have xtx inverse times xt times the expected value of that particular vector y. Now keep in mind what this model for multiple linear regression is assumed to be appropriate. Therefore, this variable y satisfies the linearity property. That is, there exists that representation for y, in particular that y is going to be equal to x times beta, and y hat, for example, is x beta plus epsilon. So once we substitute that in, we're going to have xtx inverse times xt times x beta, and then we can reassociate these xt's and x's together, and notice that the inverse of that matrix is sitting right next to it, so that we have just the beta term there, and we have that expected value of beta hat is equal to beta. Therefore, beta hat is an unbiased estimator of our coefficients for a multiple linear regression model. Now, although it is unbiased, so although beta hat is an unbiased estimator of beta, it still comes with error. Right? It still comes with error, and sometimes we refer to that as the standard error of the random variable beta hat. So let's see if we can find a nice representation for that standard of error, and as usual, we're going to be starting with the variance of that random variable beta hat. So this is going to be equal to the variance of xtx inverse xty, and keep in mind that is a constant as far as variance is concerned, and once we factor out, that's going to be equal to squared, the squared value of that particular matrix. Now, it factors out a little bit differently than usual, especially since we're working with matrices, but on the left-hand side, we're just going to be left with xtx inverse times xt, and then times the variance of y, and on the right-hand side, we're just going to have the reversal of that particular expression. So that's going to be equal to the transpose of x transpose, so it's just going to be equal to x, and then we're going to have x transpose x inverse there. Right? So once we have that, notice that y again satisfies the assumptions of the multiple linear regression model, else you can't really find a nice beautiful representation, but keep in mind it satisfies the homoscedasticity assumption for a multiple linear regression model. That means this is just equal to sigma squared, and that's just a number. So that means this is just going to be equal to sigma squared times those two matrices multiplied together. So xtx inverse xt times xt x inverse, and notice that we can associate these two matrices together, and notice that its inverse is sitting right next to it, so they just cancel out to be the identity matrix. So what kind of thing are we left with when those things simplify? So we're left with the variance of beta hat is equal to sigma squared times xtx inverse, right? And we're assuming, of course, that xtx is an invertible matrix, right? So this is a matrix. And keep in mind, the expected value of beta hat equals beta. This is a vector. So if I want, for example, the variance associated to beta hat 1 or beta hat 3 or beta hat 0, where would I find it inside of this matrix? So what exactly is the dimensions of this matrix? We should be able to show that if you have p predictors, then this is going to be a p plus 1 by p plus 1 matrix. So it's definitely associated to our particular predictors. Now, this matrix actually has a special name, and we're going to abbreviate it as the covariance of beta hat I and beta hat j matrix. Some people will call it the covariance matrix, and again, this is a p plus 1 by p plus 1 matrix. Now, what is so special about this, and how do we get the variances of our individual estimators? So keep in mind that when I is equal to j, That's going to give us, for example, the covariance of beta hat k and beta hat k. The covariance between a random variable and itself is actually equal to the variance of that random variable. So that means this is associated to the diagonal entries of our covariance matrix, right? So if I want to find the variance of a particular element, so that means the variance of a particular beta hat k is going to be equal to the kth diagonal entry of sigma squared xtx inverse. And therefore, the standard error associated to this particular estimator is going to be equal to the square root of the kth diagonal entry of the matrix sigma squared xtx inverse. And that's how you can find the standard errors of each of these terms. Now, once you actually start working through examples, you typically will see that the standard error for the intercept term, beta hat 0, will be usually higher than the others. Don't be shocked, that's typically normal because usually the units for the intercept are not in the same exact units as our coefficients of our predictor terms. So just keep that in the back of your mind when you start analyzing these things. Before we get into a worked out example of multiple linear regression, I just want to mention one quick thing, and that's the R-squared value for a dataset and also a multivariable dataset. So remember, we actually derived that the R-squared value for a simple linear regression model or a bivariate dataset is just the model sum of squares divided by the total sum of squares, which we can write in an alternative way as just the total sum of squares, which is just the variance of our response variables times m minus 1 minus the SSE, the error sum of squares, all divided by SST. And we can actually just write that as 1 minus SSE all over SST. Now I'm going to mention a brief theorem here, and I'm not going to prove it, but if you look at the formulas, you might be able to sort of see why this is the case. Let's assume that S is a subset of a population P, and let's assume that MP is a multiple linear regression model with P predictors, and MP plus 1 is a multiple linear regression model with the original P predictors and another predictor, even if it is meaningless. Generally speaking, you should still be able to calculate the R-squared value for these models. You just need to calculate the SSE, the SST, and subtract that by 1 for each of the models. And you should be able to compare them, which one's bigger, which one's smaller, or possibly they could be the same exact thing. But always, the R-squared value for the P predictor model is always going to be less than or equal to the R-squared value for the model that has more predictors. So adding more predictors always increases your R-squared value. And technically speaking, you can add infinitely many predictors to your model, and the R-squared value will get closer and closer to 1, and that's usually what we refer to as overfitting, which is definitely a bad thing. So therefore, increasing models will always make your R-squared value closer to 1, which some people view as making your model a little bit more accurate, but no, that's just a theoretical consequence of the R-squared value. So in order to sort of adapt for this issue, for example, what if this new predictor value or new several predictor values are useless, is it possible that we can sort of have a R-squared value that sort of doesn't change and actually is more well representative of the goodness of fit for our multiple linear regression model? And one of the common fixes is what we refer to as the R-squared adjusted value. So instead of 1 minus SSE over SST, what we're going to do is 1 minus MSE all over MST, right? Where MST is just going to be equal to the SST divided by n minus 1, which is just going to be equal to the variance of our y values, right? So if you sort of look at this formula in a little bit more careful eye, that's just n minus 1 divided by n minus p minus 1 times 1 minus r squared, once you work out the math. So you see that as p sort of gets bigger, this term is going to get smaller, that term is going to get bigger, so it sort of balances itself out there. But this is a more suitable alternative for a goodness of fit metric, but there are of course several others that we may talk about a little bit later. One quick thing that I want to mention before we get into the example is the following thing, and some people definitely get a little bit confused with this particular thing. Keep in mind the r-squared value is always going to be between 0 and 1, even for the multiple linear regression case, but you actually do not get this result for the r-squared adjusted value. So one can show that if the r-squared value is actually close to 0, then the r-squared adjusted value may be negative. So it's possible for the r-squared adjusted value to be negative if your r-squared value is extremely close to 0. And via this formula, you should be able to pick some numbers out that are actually possible in order to generate a negative number for the r-squared adjusted value. Now that we have all of the important things for multiple linear regression model discussed, for example, the assumptions, how to calculate your beta coefficients, and how to calculate your standard error for each of those coefficients, and also how to calculate this goodness of fit metrics, r-squared and r-squared adjusted, let's get into a numerical example to sort of see how to put this in practice. Let's assume that you're interested in trying to predict happiness via the two predictors, hunger and sleep. And let's assume that you survey 4 individuals and get these particular results where hunger is in a continuous spectrum, say from 0 to 100, and sleep is measured in hours from 0 to, I guess, positive infinity if you're sleeping really, really long. Right, and let's assume that happiness is also on a continuous scale from 0 to 100. Now, you could of course use several other predictors, x1, x2, down to say x50. You could of course not be using hunger and sleep. You could not of course be trying to predict happiness, and you definitely should be using a lot more than 4 data points for this particular model construction. But I'm just keeping things a little bit more simple, just to sort of show you how the inner workings are sort of going about. But once we get to, for example, our implementations of this, then of course we have a little bit more flexibility, since we're not going to be too scared of the math that goes behind it. So the first thing that we need to do is define our y, x, and beta vectors. So since we have x1 and x2, we have 2 predictors. That means our model is going to have 3 coefficients, beta 0, beta 1, and beta 2. So our beta vector beta is going to be the 3 by 1 vector, beta 0, beta 1, and beta 2. And our response vector y is going to be equal to 52, 43, 39, and 35. And let's assume that we keep in this order. So our data matrix x is going to be equal to, so keep in mind the first column is for beta 0, the second column is for beta 1, and the third column is for beta 2. So the first column is going to be all 1s, since we have, for example, beta 0 times 1. And then we're going to have 3, 5, 8, and 14. And then we're going to have 5.8, 5.1, 3.6, and 3.2 as our data matrix X. So the next thing that we need to, for example, figure out is this data set good to work with? So let's just make a quick note before we continue with these calculations. So if we slightly change the X matrix, the values of beta hat should not change as much, right? So it should not change as much. If they do, the model is what we call an unstable model, and the matrix X is called ill-conditioned. Ill-conditioned. So for example, if we change, for example, these two values and calculate the new beta hat coefficients, do they change a lot? If so, the whole entire matrix is what we refer to as ill condition. So in order to analyze the stability of our linear regression model, and you're going to need this once you find, for example, the inverse of XTX matrix, is to find the singular value decomposition of our matrix X. So if you find the singular value decomposition of matrix X, keep in mind the singular value decomposition is always going to be on the form UdV transpose. The matrix that's going to be of useful to us for analyzing this is going to be the matrix D. So for example, for this particular matrix X, we're going to have U times 18.6800, 5.630, 0.13, and 0. Keep in mind this has the same exact dimensions as your original matrix X, and keep in mind there's going to be a V transpose here. So our singular values are located on the pseudo-diagonal entries of this particular matrix, so we should be able to calculate the condition number for this matrix X and see if it is significantly high. So the condition number for matrix X, keep in mind, is just going to be the maximum singular value divided by the minimum singular value. So that's going to be equal to approximately 18.68 divided by 0.13, which is approximately equal to 141.40. So the next question that we need to answer is this condition number super high for us to be concerned? So a general rule of thumb to help us decide is the following little mechanism. So the output relative error, one can show, is always less than or equal to the condition number times the input relative error. Now, in terms of the things that we have control over, we typically have control over the things for which we're actually calculating, and the output error is sort of what we want to desire to be relatively small. So we desire this to be small. So let's assume that the relative output error is represented by, for example, epsilon subscript O, and the relative input error is abbreviated by epsilon subscript I. So this is not the same epsilon as residual epsilon. This is just going to be error epsilon. So we have epsilon 0 is less than or equal to the condition number times epsilon input, right? So let's assume that the output we desire is going to be less than 10 to the minus third. So this is how much we want this to have. And let's assume for our input, we are guaranteed that the error is less than 10 to the minus 16. So this is what we have. So therefore, what condition number is the maximum amount that we can have for this data matrix X in order for us to get this output error to be less than or equal to 10 to the minus 3. So if we solve this particular equation, we're going to have 10 to the minus 3 is less than or equal to the condition number times 10 to the minus 16. And that means that 10 to the power of 16 minus 3, which is 10 to the 13, is an upper bound for that to occur. That means as long as the condition number is less than or equal to 10 to the power of 13, then life is good for us in terms of getting that error that we want. And since our condition number is only 141.4, that's definitely less than 10 to the power of 13. So this model is stable as far as our criteria is concerned. Another thing that we also need to be able to check is to see if the matrix XTX is indeed invertible, and in particular that the determinant is not equal to or close to 0. So the determinant of the matrix XTX, one can find, is approximately equal to 193. So that means a unique solution for our betas exists, which is actually a very good thing. So therefore, beta hat is going to be equal to, again, xtx inverse times xty. So once you find the inverse of that xtx matrix and then multiply that by xt and then multiply that by y, you will be able to get the following 3 by 1 vector, which is approximately equal to 24.07, negative 0.24, and 4.60, which corresponds to our elements beta hat 0, beta hat 1, and beta hat 2 for our model parameters. Therefore, our predictor model is going to be approximately equal to 24.07 minus 0.24x1 plus 4.60 times x2, and this is our model for predicting happiness given a level of hunger and a level of sleep. Now, just a couple things to mention. Notice that the coefficient associated to x2 is substantially larger than the coefficient associated to x1. Therefore, one can at least qualitatively see then that the sleep predictor has a more impact on predicting happiness for a set of individuals based upon the data set for which we have collected. Now that we've constructed our multiple linear regression model based upon this data, now we need to answer the question, is this really a good model for predicting happiness via the predictors hunger and sleep based upon the data for which we have collected? So the first thing that we need to do in order to answer this question is to calculate the error sum of squares. Keep in mind the error sum of squares is minimized via this approach, and one can show that this is going to be approximately equal to 14.53. Once you have your error sum of squares, then we can calculate the MSE, which keep in mind is an approximation for sigma squared, and it's going to be equal to the SSE divided by n minus the number of predictors minus 1, which is again approximately equal to 14.53 only for this particular case. Therefore, an approximation for sigma is going to be equal to approximately the square root of MSE, since MSE is the unbiased estimator for sigma squared, and that's going to be approximately equal to 3.81, which is relatively small, which typically is a good sign if you want to sort of minimize the standard error for each of these parameters. Now let's actually look at the standard error for each of our individual elements. So one can show that again the standard error for beta hat k is going to be equal to the kth diagonal element, so the kth diagonal element of the matrix sigma square root of xtx quantity inverse, right? And one can show that the diagonal elements of that 3 by 3 matrix is going to be approximately equal to 28.46, 1.17, and 4.55. And keep in mind the first is associated to beta hat 0, and the next is beta hat 1 and beta hat 2. So as usual, we see that beta hat 0 is really relatively big, but that's not usually the concern we have. This beta hat 0 is just absorbing the variation of other variables that we are not taking into account for our particular model, but this 1.17 and this 4.55 definitely is what we need to focus on. Keep in mind that second parameter associated to, I think it was sleep, has the larger standard error, and it's actually generating the most impact for our data. So although it is impacting the data, if that is truly wrong, that's definitely driving the inaccuracy of our model up. So you definitely need to be careful when you see a high impact factor of your particular coefficient, and the standard error is also pretty substantially high. Now, once we have our sigma and our SSE and our MSE, the next thing we need to calculate, for example, is our SST. So keep in mind our SST is going to be equal to the variance of our response variables times n minus 1, and then from it you can calculate, for example, the SSM, which is just going to be equal to the SST minus the error sum of squares. Right? And one can find that the SSM is approximately equal to 144.22 for our particular data set. And then similar to simple linear regression, the Test Statistic, which is going to be associated to testing whether this model is good, is going to be equal to the MSM divided by the MSE. And for our particular data set, that's going to be equal to approximately 2.4815. Okay, so then we need to figure out, okay, is this substantially large, or is this substantially small? So this is going to be associated to an F distribution, and the degrees of freedom is going to be equal to P comma n minus P minus 1 for the general case. Because MSM has P degrees of freedom, MSE has n minus P minus 1 degrees of freedom, therefore this is going to be our test statistic. And this is going to be a one-tailed test, so our alpha region is going to be located in that right tail. Right? So one can show that the p-value of getting our test statistic 2.4815 or something more in favor of the alternative hypothesis is going to be approximately equal to 0.4095. And this is typically larger than most alphas that people choose, especially those of you who always love to choose 5% as your p-value. But even if you choose, for example, 20%, it still has the same exact conclusion. So what is the conclusion when our p-value is greater than our alpha value that we have chosen? That means we're going to fail to reject the null hypothesis. But what is the null hypothesis that we're actually testing here? The null hypothesis is that the coefficients beta 1 and beta 2 are both equal to 0. So since we are failing to reject that null hypothesis, that means we have evidence to believe that this is indeed true. Although it doesn't imply that it is true, we have evidence to believe that it is true. So that means what? That means we have evidence to believe what? That our model is not good for predicting happiness based upon the two predictors of sleep and hunger, but mainly this is due to the fact that we only chose four particular sample sets for generating our particular model. Now there are several other little things that I've sort of skipped over. For example, the variance inflation factors. How do we know that beta 1 is actually a good predictor to include? Maybe we can throw out beta 2 and just keep beta 1. Maybe we can throw out beta 1 and just keep beta 2. Or maybe we should be including predictors, like how do we decide all of those things? We're definitely going to get to each of those questions a little bit later and study the multiple linear regression model and its assumptions and its assumption testing a little bit later as well. But for now, those are just the basics associated to multiple linear regression. I hope you enjoyed this video, and I'll see you in the next one. Take care.